Hey all, and welcome to your last test for Convergence, and this is the one that I see students tend to use a lot, and the main reason is that it's generally the one that students tend to remember because we do it last. But I'm going to talk to you about some of the reasons when to use this one, and also to make sure that you're practicing all of our tests, which are going to be a really important skill that you're working on for this coming part of the unit, which again, you have another practice day on Thursday. Make sure you turn in those odd number problems checked in the back of the book, corrected if necessary. So the ratio and root test, these are two separate tests, but they are incredibly similar. And the ratio test says that if you have a series and the absolute value of the limit as n approaches infinity of just two consecutive terms is equal to a number, then if that number is less than 1, it's convergent. If that number is greater than 1, it's divergent. And if it's equal to 1, it's inconclusive and you have to use a different test. Now, the times that I recommend that you use the ratio test are when you see factorials. And you're going to start seeing a lot more factorials in these series for this chapter, this section. And that just mainly tells you, oh, I want to use the ratio test. So whenever you see factorials, that is a sure sign to use the ratio test. So what I'm going to do is I'm going to start by setting up my limit. So my limit as n approaches infinity of the absolute value of a n plus 1 over a sub n. Now, the absolute value here means that you can cancel out any powers of -1, because that doesn't change the absolute value, it just makes it positive or negative, which absolute value is always positive. So in this case, we're looking at the limit as n approaches infinity of 1 over n plus 1 factorial for the a sub n plus 1 in the numerator, and 1 over n factorial in the denominator. Now, what I like to do at this part of the ratio test is I'm going to say, well, that is n plus 1 factorial times the reciprocal. You know, because if you want to think about it as divided as 1 over n factorial, I'm going to change this to multiplication, multiply by the reciprocal. So I end up with the limit as n approaches infinity of n factorial over n plus 1 factorial. And this is why factorials are really good for the ratio test. Now remember, with factorials, I'm going to expand this out. It's 1 times 2 times 3 times 4 times 1, all the way out to n minus 1, n. Now the factorial in the denominator, same thing. 1 times 2 times 3, that's how all factorials start. And this goes all the way out to n plus 1. The term before that's n, the term before that is n minus 1, and so on. Now the reason that I wrote this all out like this is you get a lot of canceling. n in the numerator and denominator, gone. N minus 1, all of the intermediate terms all cancel out, and we're just left with limit as n approaches infinity of nothing in the numerator over n plus 1 in the denominator, like so. Now, when I plug in infinity, you get 1 over infinity, which is 0. And since 0 is less than 1, right, that's our term right up here, we know that the series is then not only convergent, I can't spell today, converges, and because of the alternating section here, and we took the absolute value, we can even say that it absolutely converges since we removed the alternating section, which in this case is -1. So recall from previous, the alternating series is that if you take away the alternating property and it still converges, that's called absolutely convergent. If you need to use a different test, so in this case, if this test had been inconclusive, I would have used the alternating series test, and that would have told us that it was conditionally convergent. So the ratio test, the reason we do these together is that they operate by the same rules. There's a typo here. So it's that as you have the series, and as you take the nth root, so that should have an nth root there. If that equals a number, and again, if that is less than 1, it's convergent. If it's greater than 1, it's divergent. And if it's equal to 1, it's inconclusive, and you have to use a different test. Now, the reason that we're going to use the root test here is, because I just fixed the typo, is that if you have a bunch of stuff to the power of n, so power of n, but not geometric. So in this case, it's got a power of n, but there's variables inside. Like if this had been just 2/3, I could have said, oh, well, that's geometric, and that r is equal to 2/3. It's convergent by that means. But if you have a power of n and not a geometric series, that means that you should use the root test. And the reason for this is that when I set up my limit, as n approaches infinity of the nth root of the series, so 2n plus 3 over 3n plus 2 to the n, and you'll notice here, oh, the nth root and the power of n cancel out. That's why we want to use the root test for these types of problems. So then the limit as n approaches infinity, in this case, 2n plus 3 over 3n plus 2. Now you'll notice here there's an absolute value, and we could include that here, but you'll notice that we have only positive values. So that's just fine. If there were negative numbers, you could do some canceling out, just like we did in our ratio test. Now, since we're going towards infinity, the plus 3 and the plus 2 don't make a difference. We can drop those lower degree terms. And that leaves us with the limit as n approaches infinity of 2n over 3n, which is 2/3. 2/3 is less than 1. So using the root test, that means that the series is convergent. And it's absolutely convergent again because we don't have to worry about any alternating section here. So absolutely convergent. Here we've had an example of both. If you want to see more examples, nominate questions in the forms that are attached to each assignment, and I go through those every week, a couple times each week, to go through those problems, show you how to solve them, and that can be especially helpful when you're looking at your series review time on Thursday. Look forward to hearing from you if you have any questions.